Okay, the first video was cut off a bit. We are back, and as I mentioned in the previous slides, Pythagoreans were secondly known for discovering, so to speak, the existence of irrational numbers and or irrational quantities. Although their proof of the existence of such numbers or quantities had a very geometrical flavor. So what do we mean by irrational numbers in this case, and how does one go about it? We have, let's start with two line segments, AB, and another line segment CD. So let me call this segment AB, and this is the segment CD. Okay, so let's say that segment AB is not cut off, but if you can divide it in a number of smaller segments, and I have more or less the same thing for segment CD. Alright, let me just draw this other segment. Let me call it EF. Alright, so we say that two line segments AB and CD are commensurable if there exists a smaller segment EF that goes evenly into both AB and CD. What does that mean? That means that for some whole number P and Q, AB is composed of P segments EF, and CD is composed of Q segments EF. Let me just write that down. So two line segments, AB and CD, and CD are said to be commensurable if there exists, for those of you who haven't seen this before, this type of notation means there exists. If there exists a smaller segment EF, that goes evenly into both AB and CD. Into both AB and CD. With other words, for some integers P and Q, this is the same as saying that P and Q are elements of the set of integers. This is notation for the set of integers. Again, for those of you who are not familiar with such notations, this only means that P and Q are any two integers. AB is composed of P segments congruent to EF or equal to EF, congruent to EF, while the line segment CD is composed of Q such segments. So this means that the segment AB is equal to P times the magnitude or the length of the segment EF, and CD is equal to Q times the magnitude of EF. And so the magnitude or the length of segment AB over the magnitude of segment CD is equal to P times EF, this is small p, over Q times EF, and that is the same as saying P over Q. And since P over Q is the ratio of two positive integers, we say that the length of commensurable segments is a rational number. So intuitively, the Pythagoreans felt that any two magnitudes are commensurable. So any two magnitudes or line segments or lengths, any two magnitudes are commensurable. Okay. With other words, given any two line segments, they did not doubt the existence of another segment EF dividing evenly into both AB and CD. There exists another segment dividing evenly into both in the first two. So that is the concept of commensurable quantity or length. However, tradition credits the Pythagorean Hippasus with discovering that the side of a square and its diagonal are not, in fact, commensurable. So tremendous was that actually was profound. It had profound consequences for the entire Pythagorean society for two reasons. First, it shattered all Pythagoreans' proof that relied in supposed commensurability of all segments, and secondly, it had a very unsettling impact upon the supremacy of whole numbers. Let me erase this so I can move on with this concept of existence of an irrational quantity. Again, I'm giving you a minute less than a minute to take a look at this or photograph it before I erase it. what hypasus meant was the following. Should you have a square of with sides of length 1, whatever 1 is, by 1 here we mean unit, a measure. Measure of unit. Okay. So if this is a square with sides of length 1, then as we know from Pythagorean theorem, then the diagonal of a square, or rather the hypotenuse of this right triangle, is simply the square root of 2. But the square root of 2 cannot be written as a rational number of the form p over q. So square root of 2 cannot be written as the ratio of two integers. As the ratio of two integers. P over q. Hence, it has to be, numerically speaking, an irrational number. So, hence, numerically, must be an irrational number. In fact, the legend has it that hypotheses were actually thrown in a river of sword just for daring to actually say such a thing. As I mentioned before, a lot of the Pythagorean proofs were simply based on this idea that every magnitude is commensurable, and the existence of whole numbers and rational numbers and whatnot. So this was obviously a big deal. The next subject of prominence in mathematics after Thales and Pythagoras was Hippocrates. Now, there are two. We should not mix them up. There is Hippocrates of medicine, and there is an Hippocrates of mathematics. Hippocrates of mathematics was born in the island of Chios in Greece, whereas the medical one was born in a nearby island of Kos. To Hippocrates is attributed the earliest mathematical proof that has survived in some authentic form. Hippocrates is remembered for two contributions to geometry. So Hippocrates, let me just write this. Okay. It is known for, as I said before, two contributions to geometry. One of them was the first composition of elements, the book Elements. Of elements. And the next contribution the one that he is more known for is the so-called quadrature of the lune. Quadrature of the lune. So what do we mean by quadrature of the lune? I'm going to write in the next slide what we mean by this concept of quadrature, and then we will talk about the quadrature either of the lune or other geometrical figures in the next lecture. So that will be the subject of the next lecture. So, quadrature of the lune. Well, let me just write what I mean by quadrature. I'll erase this. Okay. So, remarks on quadrature. Quadrature. The quadrature actually means the squaring of some geometrical two-dimensional shape. What does that mean? Let me just write it here. So the quadrature or squaring, I'll explain what that means in a bit, of a plane figure is the construction using only compass and ruler with no markings in it, and that's important, at least for the next few chapters. Whenever we say constructing a plane figure, I mean only using compass and a ruler with no markings in it. Only compass. Okay. So the quadrature of a plane figure is the construction of a square having area equal to that of the original plane figure. If the quadrature or squaring of a plane figure can be accomplished, we say that the figure is quadrable. Why is this important? Well, not only from the geometrical point of view and the beauty of geometry and whatnot, but even from the practical point of view, should you have a plane figure and you want to find the area, and you want to find the area of a lot of geometrical figures, two-dimensional ones, especially when it comes to agriculture and whatnot, it would be a lot easier, if possible, to square it, or it will be a lot easier if this shape in question is actually quadrable, to find the area of that shape than finding the area in some other ways. For example, if you have something that looks like this, and you want to find the area of it, if you could build a square that would have exactly the area of this, then you're done, because you know how to compute the area of a square. Whereas just finding the area of this plane figure, it on its own right, just by not using something that helps, some other figure that is much simpler than this, it's rather hard, or at least for early Greeks, it was impossible. Unless, I repeat, it was proved that this particular shape was quadrable, as we will see in the next lecture, proving that a two-dimensional shape, not just any, but we'll start with the simple ones in the beginning, is not exactly an easy feat. But as I said before, this will be the topic of our next lecture. Together with this video, I will post 2 or 3 problems that are related to the things that I talked about in this lecture, and see if you can work on them. As I mentioned in our first meeting, these homeworks are not to be collected immediately, or should I collect some of those, I'll let you know in advance which ones it will be. But feel free to use the office hours twice a week to address these problems. If you have any questions about them, or if you don't know how to do them, or if you tried and didn't get anywhere, whatever the case may be. So long everyone, until next time.